Hello and welcome back to our discussion sessions. So far we have discussed the engineering materials and material properties. Now we will start discussing metal machining. This is our second module. Here we will discuss different kind of machining operations, conventional machining operations, how they are conducted and what is the physics behind the processes, okay. How the forces are obtained, how the forces are related to other parameters like machining parameters, on which factors the forces depend and the power consumption depend. To begin with, let us discuss one thing and get it cleared, that any part can be manufactured, fabricated in three ways. It can be fabricated without changing the initial volume of the material, raw material. So, those processes are called the constant volume operation or constant mass operation. Okay. The mass is not changed, rather. Those processes, as you know, those are casting, metal forming, etc., where the final mass and the initial mass there is no difference. Okay. We are not removing any material, excess material. The parts can be fabricated by removing excess material from the workpiece surface. So, those processes are called the machining processes. Okay. That exactly we will be discussing in our discussion right now. And the third process is when the material is added to the initial material, that is to the blank. Okay. So, those processes, as you understand, that they are the welding, the rapid prototyping, for example, these are the recently developed 3D printer you must have heard. So, there layer by layer the material is added, okay, on the base and the final product is made layer by layer. Welding, where the other parts are attached, joining, for example, nut is joined to the bolt, okay. So, there the mass is added. Now, these are the three processes, and now let us see that for any fabrication, now you get a part, final product, okay. How many engineering disciplines are involved in the final process or to get the final product? First of all, we will start from the ore, all right. So, that ore is in the mother earth, somewhere we do not know. So, we involve geologists, geophysics specialists to find out where exactly the ore is available, let us say iron ore, okay, or for that matter aluminum ore, copper ore and other materials. Now, when the geologists and geophysicists they find out the place, it has to be extracted, okay. Then the mining people are involved there to extract the ore, okay, and transport it to the metallurgist people. So, metallurgist people in its turn they melt it, segregate the metal from the ore and they get the kind of raw material, okay. So, the raw material, if you see here, if you see the slides, raw materials may be of this nature. It can be of round shape, okay, like that. It can be a square shape, okay. It can be a rectangular shape, for example, okay, or it can be of this shape, let us say angles, okay. It can be of this shape, for example, all right. So, all these are the raw materials and they are produced after the the ore is melted, the metal is segregated from the ore, and the long rods like this, they are actually produced like this, okay, very long rods and so on, okay, let us say like this and so on. Now, these raw materials, they go through the kind of a process. Okay. So, this process that they go through, all right, let us say this is the process, and in this process, the apart from the raw material, let us say this is the raw material. Okay. Apart from the raw material, we have to have the certain kind of information. Okay. We have to have certain sort of energy, all right, and as the output we will have the final product or finished product. Okay. We will have some waste, we will have some energy in the form of, it may be a heat energy, where the mechanical energy that you are putting in the process, that is converted to the heat output. So, that is also a kind of an energy which we are getting at the output of the process. Okay. So, these are the processes which we call as the manufacturing processes. So, it can be a, as I said, the constant mass operation, it can be material removal operation, or it can be the mass addition process. Okay. Now, in here we have somewhere the role of the machining, because we will be discussing the machining processes mostly here. So, let us see what is the position of the machining here. Now, this is the raw material, and let us say from here the component 1, component 2, and there are 6 components altogether, okay, from this raw material. Now, component 1, let us say, it will go through the casting, and then it will go through joining, finishing or assembly to get the final product. Similarly, component number 2 will go through casting, then it will go through machining, then it will be going for the joining, finishing or assembly. Similarly, you can see that all components need not to go through a particular process or all the processes. Okay. For example, let us take the component 1. You know that there are precise casting, okay, lost wax method, investment casting, I mean. So, those or you know, high pressure casting. So, there after the casting, the process, the part quality will be final and the dimensions will be adhered to. So, therefore, after the casting, particularly for those castings where we have the very precision in the process. So, there we do not need any other process. So, it will directly go for the joining or go for the assembly. At the most it can go for finishing, or it may need a component may need after casting some sort of machining, okay, because after casting either the sides are not exactly perpendicular or the surface finish is not very good and so on, or some dimensions are not proper. So, the machining is involved in correcting or finishing the casting part, all right, or it may need even any component may need even primary forming, okay, and then secondary forming, and then it can only go for the assembly or joining or finishing, and then it will come as a final product. Now, that means you can see that first of all not all components need to be going through all these processes, and here is the machining process, and the role of machining process in these manufacturing processes, okay, like casting, primary forming, as we said, this is the constant mass operation, machining is the material removal operation, secondary forming is like primary forming, it will be the constant mass operation, joining, assembly, these are of course mass addition processes. Okay. Here also The joining means we are talking about it may be even welding also, and then the final product will be obtained. Okay. So, therefore, the role of machining in the manufacturing processes is really great, in the sense that machining maybe if I quote maybe 80 to 90% of the product in the industry, they go through the machining. Okay. Let us see what is that. In machining, if we have to define the machining, the shape, size, finish and accuracy are obtained by removing excess material from the workpiece surface. So, initially I said that the machining process is the material removal process, and this is the process in which the shape, size, finish and accuracy, these are obtained by removing the excess material, and that excess material is removed in terms of small chips, okay, with the help of a tool and with the help of a contrivance, that is a machine which is called a machine tool. If it is a turning process, the machine tool is the lathe machine, milling process, it is a milling machine and so on. That we will also see those machines in the laboratory. Now, various surfaces are obtained as an interaction between the workpiece and the cutting tool with the help of a contrivance, as I said, known as a machine tool. Now, what does it mean? Meaning, depending upon the relative movement between the tool and the workpiece, we can get different surfaces. Now, I will give you some examples. Let us say the workpiece is rotating either clockwise or anti-clockwise, and the tool is moving parallel to the workpiece surface. As you know that in that case you can get an external cylindrical surface or internal cylindrical surface also. Okay. For example, in case if the tool is a boring tool which will be attached to the tailstock and it will not be rotated, it will be moving along the I mean as parallel to the axis of the workpiece. Or if the tool does not move parallel to the workpiece axis, but at an angle, then you know that we can get an external taper surface or an internal taper surface. Okay. If the tool moves perpendicular to the workpiece axis, then it is a facing operation. So, what we get is a flat surface, as a matter of fact. Okay. We can also have a knurling surface, knurled surface, we can have a threaded surface and so on. So, these are the processes that we can get by particularly turning process, okay, depending on the relative movement between the workpiece and the tool. Similarly, we can get a hole, either it is a blind hole or it is a through hole by means of the drilling, okay, by means of reaming, the tapping. We can get an internal thread, for example. We can get a flat surface, an inclined surface or a grooved surface in case of shaping or planing. We can get a flat surface, contour surface in milling and so on. So, different kind of intricate surfaces can be obtained by removing the excess material from the workpiece surface and in terms of the small chips with the help of the tool and the contrivance. I repeat once again. So, in this slide, if you see that this is the turning process and here is the tool removing the excess material in terms of small chips. Okay. So, either in case of drilling, small chips is removed, or in case of the milling, or in case of turning. So, what we are getting is by removing that we are actually having this is the finished surface, this is a new surface. Okay. So, let us say this is the cylindrical job and here we are actually turning this cylindrical surface to reduce the diameter from D0 is the initial diameter and D I think F, which is the finished one, this is the finished surface diameter. Okay. In doing so, we have to rotate the job if it is turning and move the single point turning tool along the axis or parallel to the axis of the workpiece. Then only we will get this kind of a surface. All right. Now, this much is removed from both sides. So, this is the difference between the initial surface and the finished surface, and that divided by 2 will be, because in both sides will be the depth of cut. All right. This is the here it is shown that how this uncut thickness can be obtained. Okay, that we will discuss in more details later on. Now, here if you see that this is the straight turning, as in this case this is the grooving. So, in case of grooving, as you can see, the tool is given a feed, okay, which is perpendicular to the workpiece surface. In this case it is parallel to the workpiece surface. Okay, this is the feed direction. And what is feed is that in one revolution of the workpiece, how much linear distance the tool is covering. Okay. So, in each one revolution of the workpiece, how much millimeter the tool is moving, okay, through the workpiece material, that we mean as the, that we designate as the depth feed. Okay. And therefore, here the feed direction, as you can see, is perpendicular to the workpiece axis. This is an example of drilling. So, in case of drilling, this is different than the turning. Okay. In case of drilling, the workpiece does not rotate, workpiece is fixed on the table, and the tool, which is the drill, this rotates as well as it penetrates. So, this penetration is the thrust force which is imparted to the tool, that is the drill, and it also rotates. So, everything that is the feed motion and the cutting motion will be given to the tool. Now, what I mean by cutting motion is, if you see here, this is the diameter. Okay. So, depending on the number of revolution n, that is the RPM, revolution per minute, we can actually find out what is the cutting speed. So, therefore, the cutting speed is decided by the diameter, initial diameter of the workpiece, and this is given, as you know, that this V cutting speed is pi into diameter into the RPM. Okay. So, depending on the RPM and the revolution of the workpiece and the diameter of the workpiece, you can actually find out what is the cutting speed. Now, in case of drilling, the cutting speed will be given to the drill rotates. Okay. So, here also, depending on the RPM of the drilling machine or the drill at which frequency it is rotating, okay, again RPM, and the drill diameter, you can find out what is the cutting speed, that means at which speed the drill is rotating. All right. Similarly, in case of milling, if you see here, this is the milling cutter. The milling cutter is mounted on the arbor. This is the arbor of the milling cutter, okay, or the machine. Here it is horizontal, here it is vertical. So, as you know that these kind of machines where such operation is performed is called the horizontal milling machine, and this kind of operations performed on the vertical milling machine. Okay. So, in this case, this is called the end mill cutter, all right, and this is called the slab milling. Okay. So, here if you can see that these are the spiral milling cutter. The teeth are not straight, but they are spirally located at the periphery of the work of the tool. Okay. So, here in this case, it is a flat surface which is produced. Here you can see there is a pocket is produced. Okay. It may be a blind, it may be a through, and so on, and here the hole is produced. So, by drilling you can actually make an internal hole. So, that internal hole may be through hole or it may be a blind hole, that means it may not be going along the full length of the workpiece. So, it is a blind hole. All right. Now, what are the advantages and disadvantages of machining? Now, in advantages, there are a variety of work materials can be machined. All right. It is a hard material can be machined, soft material can be machined, all right, plastic materials can be machined, and so on. So, which may not be possible in some other processes. Okay. Most frequently used to cut metals, okay, to remove excess material from the metals. Second point is that variety of part shapes and special geometric features is possible, such as screw threads, okay, accurate round holes, very straight edges and surfaces. So, these are the advantages that see you understand that in the case of the metal forming, for example, okay, or casting, for example, you can actually cast threads. You can actually make threads in the metal forming process by cold rolling or so. but the accuracy that you will be getting in machining will be higher than in case of cold rolling or thread obtained by casting, all right. Or after the casting, it has to go through the machining to get the proper accuracy. That is what is the machining important is. Now, the good dimensional accuracy and surface finish in machining generally performed after other manufacturing processes such as casting, forging and bar drawing. As I was telling that initially it will be casted or bar drawn, okay, or forged, and then the final shape, final finish, final accuracy will be given by machining normally. Only disadvantage is of course wasteful of material and time consuming, because it is the removal of excess material. Okay. So, for example, you want to get a part like this, okay, part like this. So, for that you have to get blank which will be of this type, let us say. So, this is the material, or this is called the allowance. This material has to be removed. Okay. So, this is the waste of material. This material is in terms of small chips that will be removed, so that cannot be used. Chips cannot be used to remelt and make, let us say, use for casting, okay. Because they are very hard material, their properties are changed, they have gone through the strain hardening and so on, which we will be discussing later on. Okay. So, this is the waste of material we are calling. In case of casting, in case of metal forming, okay, or in case of powder metallurgy, for example, this kind of situation does not arise, that no wastage takes place, and that we consider to be one of the biggest disadvantages and probably the only disadvantage in the machining, that this is the wasteful of material, and it is of course time consuming, because in case of if you want to make this material, this product in metal forming, for example, it could be made in a much easier way or much faster way, let us say. Okay. Now, what is the mechanism of machining? Now, earlier it was believed that when metal is cut, the material merely splits off in front of the tool, similar to chopping of wood. So, let us say this is a wooden piece, wood piece. Okay. So, in here this is the X, okay, this is the X and this is the wood. So, how the wood is chopped, that once you hit with the X, there is a crack here, okay, in front of the X, and that crack is propagated, and then the material is segregated from the base material. So, it was assumed initially that metal also is cut with the help of crack propagation. Okay. Crack propagation in fact helps, it was assumed. Subsequently, it was realized that the cutting of metal involved deformation process. Okay. It is not the splitting of the wood in front of the X and then propagating the crack, but it is actually some sort of deformation process. Further experiments revealed that the deformation was principally one of the shear, that is a shear deformation, okay, and that the type of chips varied with the work material and the cutting conditions. All right. Now, this is clear, and it will be also further clarified in future also, that the types of chips that you will be getting, either it is a continuous, it is a discontinuous chip, or it is a serrated chips, okay, or it is a built up edge form, that all depends on the cutting process or the cutting process parameters that you have selected. Cutting parameters we will discuss in more details later. These are the cutting speed, this is the feed, depth of cut, and those I have shown it to you, what are those parameters. Okay. Now, extensive research revealed that the process essentially involves plastic deformation. So, that deformation is a plastic deformation and fracture under the high strain rate and high temperature. Okay. So, high strain rate is imparted by the cutting force. All right. So, there is a prime mover, that prime mover through the lead screw, it moves the tool. Okay. You will see that in the lab as well. So, through that we are actually imparting certain cutting force, all right. Now, cutting force multiplied by the cutting velocity, that will be the cutting power. So, that power is given to the cutting process, so that the material is removed. Okay. So, that creates very high strain rate of deformation, and of course, high temperature. High temperature because the material is plastically deformed, all right, that is one thing, and most of the heat is produced because the material is plastically being deformed. So, that because of the plastic deformation first of all, and then of course, when the material is removed, the removed material in terms of small chips, it actually slides over the rake face of the tool, all right. So, that friction between the chip and the rake face of the tool, that creates further temperature. So, the temperature because of the plastic deformation added to the temperature because of the friction, that actually gives very high rise in the temperature. Okay. Now, therefore, when we do the tensile test, okay, particularly of a mild steel bar, this actually reveals what is deformation, what is particularly plastic deformation, because that is why I said that this has to be a mild steel bar, because mild steel bars are mild steels are, these are not the material which will break here, okay, that we have discussed in the when we discuss the materials. So, these are the ductile materials, not the brittle materials. So, therefore, the curve will go all the way to the up to the fracture, and fracture means the segregation of the excess material from the base material, from the workpiece, all right. So, therefore, this curve actually helps us to understand what is plastic deformation, and I have already explained this curve to an extent during the materials and the discussion on materials and the properties. So, I will go through little more faster, but here some of the details which we have not discussed, I would like to add here. Now, let us say this we know that point 1 is the proportionality limit, okay. This is the elastic limit, okay. Then we have the point C is the lower yield point, this is the upper yield point, okay. Then we have the E, which is the necking point, and then here it fractures, okay. Now, region OA, this exhibits elastic behavior, that I already explained. That means increase in length proportional to the applied load. So, this is linear in nature so far. When applied load is removed, the bar returns to its original position, okay, original length. Now, then comes the AB. AB, it is no more linear, but material is still elastic, okay. So, the relationship between load and extension is no longer remain linear, and the maximum load that can be applied without causing the permanent deformation. So, this is not still the permanent deformation, because even at this point, just below this point, let us say, if you remove the load, the specimen or the material will come back to the original length, let us say here, okay. So, therefore, the maximum load that can be applied without causing the permanent deformation defines the elastic limit. So, up to that, this is the elastic limit. Beyond the point B, metal no longer behaves elastically, and removal of the load leaves the bar with permanent extension. So, this is plastic deformation already starts after the point B, meaning that after point B, if we remove the load, okay, the specimen or the material will not come back to the initial length, and the permanent deformation remains permanent. If it is bent, it will be remain as bended material, okay, bent material. Just above the point B, this is called the upper yield point, and as I said that this is the lower yield point. Elastic behavior of the material ceases and yielding starts, this is called the yield point. Here the elastic behavior ceases, stops, okay, finishes. Stress at point B at here is normally called the upper yield stress and this the lower yield stress. Now, region CD here, this has not been explained because this does not happen for all materials. Okay. Yielding in mild steel is accompanied by a sudden drop in load as the yielding starts, sudden drop in load, and increase in length, as you can see C to D increase in the length, okay, at approximately the constant load. It just fluctuates a little bit, but overall almost constant load. Stress at point C is called the lower yield stress, as I said. This upper yield stress and lower yield stress is characteristic of mild steel caused by the presence of small amount of foreign atoms in the material. These foreign atoms could be carbon, okay, nitrogen, okay, etc. Most metals and alloys do not show this type of pronounced yielding stress, meaning that CD and this fall and all those, therefore, you may not see all these so prominently in the books because they show in general, and this is the case that I am showing you. This is particularly in case of the mild steel, okay, that it drops like that and then it remains the same, load remains the same, okay, and the extension happens and so on. So, this is only for characteristic for the mild steel, mind it, do not get confused, not all other materials, not all metals will have this kind of a characteristic. So, then you remember that what we have discussed during our discussion of materials and their properties, we have discussed the curve without this kind of a fall and this kind of a fluctuation in the force or in the load. Now, most metals do not show, okay, initial yielding and change from elastic to elastic plastic deformation is gradual in most of the cases. Region DE here, this region is the strain hardening region, we call it. Okay. This I have told you already earlier. Following the transition from elastic to plastic behavior, the load required for further deformation increases, as you can see this. But this increase in the load is not linear, of course, this is a non-linear, does not remain linear anymore. The material being able to withstand the increased load despite the uniform reduction in the cross sectional area is called the strain hardening. Okay. In some books you will find that this is also called the work hardening. It is the same thing, work hardening or the strain hardening is the same thing, and the definition I am repeating, I have already told you during the discussion on materials. Two opposing factors operate to determine the load required for a given extension. This is strain hardening that leads to an increase of load, and the reduction in the cross sectional area that leads in the decreased of load. Just these two factors, it is very important to understand that this is a contradictory factor. The strain hardening is there, so strain hardening increases the load, okay, because material is hardened, so more force is required to remove the material. Now, the also after the E point, the necking starts. Okay. E is the point of instability, it is also called the point of instability because afterwards the material is unstable, all right. So, after that, that means at this point of instability the necking starts, that means the material the deformation happens locally, okay, and therefore, there is a necking starts and the load required will be less. So, therefore, we are saying the two opposing factors operate to determine the load required for a given extension. Strain hardening leading to increase in the load and reduction in the cross sectional area, that is the necking, leading to the decrease in the load. Point E, as I said, that is the necking. When extension becomes large, the strain hardening is unable to cope up with the decrease in the cross sectional area and the necking starts, localized deformation. Okay. This is, as I said, that this is indicative of an instability condition, all right. This leads to a decrease in cross sectional area and the neck is developed. At point F, this is the fracture, all right. In fact, point F is I also told you earlier that this is not defined. At any point after E, the material can be segregated, material can fracture. So, that depends on, this varies from material to material. Straining takes place under a complicated and continuously changing triaxial tensile stress system from E. See, from D to E it is still non-linear, it is plastic deformation, it is a strain hardening, and it is all predictable. All right. As soon as this point starts, since the necking started and the deformation has become only localized, therefore, it is erratic and you cannot predict anything, and here from E to F straining takes place under a complicated and continuously changing triaxial tensile stress system. Okay. So, therefore, stress and strain we have to define, as we have defined also in case of materials. The mode of deformation of a material under applied load will depend not only on the magnitude of forces and the mechanical properties of the material, but also on the way in which the forces are applied and combined. Okay. It is not only that what is the magnitude, but how the forces are acting, at which point the forces are acting. Okay. Nominal stress is defined as the load divided by the original cross sectional area of the bar. Okay. So, this also we have discussed earlier also, because earlier we said that this is the engineering stress. Okay. Engineering strain, by the way, the engineering stress we said, that is also called the nominal stress. Okay. Because here we can say, see that this is the original cross sectional area of the bar. And now you know that the difference between the engineering and the true stress is that one in the case of engineering it is original area, and in case of true stress it is the area on which actually is experiencing the stress. Okay. Now, engineering strain is defined as the extension per unit original length. Again it is an engineering strain, and therefore, we have the length considered as the original length. The load extension diagram of a bar with therefore unit cross sectional area and unit gauge length is therefore the nominal stress strain curve for the material. Okay. So, we mean that here we have the load and extension, it can as well be expressed as stress here and the strain here. Okay. This is because when the load extension diagram is taken for the unit cross sectional area and unit gauge length. Okay. But in that case we have to tell that this is the nominal stress and nominal strain, or the engineering stress and engineering strain, not the true. Stress when considered as acting perpendicular to a surface, that is called the normal or the direct stress. Okay. When parallel to a surface, they are called the shear stresses. Okay. So, what I mean to say is that suppose you have a cube, all right, and it has the 6 faces. Okay. So, if the stress is like this, so this is the normal stress or normal force. I mean, this is the, let us say this is the normal force, because the stress will be because of the normal force. So, let us say if it is stress, so it will be like this, all right. And if the direction is parallel to the workpiece or parallel to the surface, this is the shear or this stress, okay, shear stress, that is the tau. This is the normal stress that is perpendicular to the face, and this is parallel to the face. So, this is the shear stress, that is what we are saying. Now, at any point in a stressed body, the stresses may be resolved into 9 components acting on the face of an imaginary cube. Which are the 9 components? Let us say we will again write that cube in a bigger way. Okay. I am exaggerating that. Okay. So, let us say we will put it in an axis. Okay. Let us say this is axis 1, this is 2, this is 3. So, here it will be delta 1 sigma 1 and delta 1 1, 2 2 normal and the 3 3. Okay. Then we will have the shear, one like this will be tau 1 2, all right. Then it will be like this, then this is the tau 1 3, 1 towards 3. Similarly, here if you see that here it will be tau 2 1, these are the shear stresses. This will be tau 2 3, this is tau 3 2, and this is tau 3 1. So, as you can see that 6 plus 3 9 components, or the 9 components of the stresses. So, 3 components will be normal stresses and 6 components will be shear stresses. The axis defining the faces 1 2 3 we have taken in this case of the cube may be chosen in any direction, okay, because that depends on us how you are choosing the either it will be like this or it will be inclined. So, that depends on how we want to define the faces of the cube, all right. For some purpose it is convenient to choose axis so that the shear stresses, in this case these 6 shear stresses are 0. The normal stresses acting are then, as many of you might be knowing, are the principal stresses. Now, Morse circle, stress circle construction is a convenient means of relating the stresses on any plane to the principal stress. So, you know the Morse circle, like if it is a circle. So, let us say this will be taken like this, okay. So, this is the stress, this is the strain, right. Now, let us say this is we will write it as a shear. So, this is normal, this is shear, all right. And if it is 2 dimensional, then this will be, let us say delta 1 sigma 3, and if it is the 3 dimensional, of course, then it will be like this, right. And let us say bigger way. So, here it will be 1 2 and 3, these are the normal stresses, these are the shear stresses. So, this is the one that we are talking about, this is the 3D, okay, and this is the 2 dimensional. Okay. So, here we have the on the periphery and this is inside, all right. The stresses on a plane will be given as a point inside this, and in case of 2 dimensional it is on the periphery of the Morse circle, that you must be knowing that. Okay. Now, if let us say L0 is the original length of a bar and L is the current gauge length after the elongation, then true or natural strain, this is called also natural strain, okay, is defined in terms of the strain increment. So, this we have seen, and therefore, I am not describing this in details. The advantage, you know, that this is logarithmic advantage, that it is additive in sequential process, and how it is additive I have already shown it to you. So, you can see it here that if the bar is strained from L0 to L1 and to L2 and so on. So, the finally what we will get is that total strain will be equal to the final length and the original length, I mean initial length. Okay. So, therefore, it is additive in the sequential process, we call it. This we have discussed while discussing the materials and their properties. Now, let us see here, this is the mechanism of plastic deformation, and we will try to explain that mechanism of plastic deformation in the atomic scale. Why it is important? Because any metal, any material for that matter will have a lattice structure. Okay. So, the lattice structure contains the atoms, and those atoms are sitting very peacefully, in the sense that they are occupying their own space, and the material is stable, or the metal is supposed to be stable. Now, if we disturb the position of the metal, position of the atom in the lattice structure, then the metal will be annoyed, meaning that they will try to resist first of all the deformation that we are trying to make. That means that we are trying to disturb the position of the atom, and position of the atom can be disturbed only with very high force, because they are very stable, and that high force is considered to be the stress that we are applying or the high strain rate that we are applying to deform the material. All right. So, when we are deforming the metal, we are also changing the position of the atoms, meaning we are shifting the layers of the atom, we are shifting few layers of the atom and so on. So, that has to be explained, that can be explained, that is deformation in the atomic scale, how it happens. Let us see. For plastic deformation to occur, it is necessary to have large scale slipping, okay, where two planes of atoms slip past each other, causing one entire section to move relative to another. Look at it here. As I said that this is the lattice structure where atoms are peacefully located in their own space. Okay. This is the distance between the atoms. So, this is called the interatomic distance. So, this is the A, all right, and this is the distance between the two layers, this is the B. And let us say now we are applying some sort of shear forces. So, this shear force creating the shear stress, and if the shear force becomes larger than certain value, okay, then only it will be able to displace two layers of the atoms as shown here. Now, let us say because of the application of the shear force, these layers, okay, this is moving with respect to another layer. It has moved, as you can see that it has moved to this side, okay, like that. So, after slipping through the distance A, all right. So, then the distance that has slipped, let us say it is A. Slip occurs more easily on certain crystallographic planes. It will not happen in any plane, that is one thing. Certain crystallographic planes, I am going to explain on which planes it is possible, only the slip occurs. That means the deformation, when you will be deforming the material, you will deform, material will be deformed on a certain in a certain fashion, let us say. So, along the certain plane, and that plane is called the slip line. That plane or the line is called the slip lines, and the plane is called the slip planes. Okay. Crystallographic planes that are farthest apart are also the ones of the greatest atomic density. Okay. Slip tends to occur on such plane since the resistance to slip is then minimum. Let me explain it to you, that where you will find the slip plane. Okay. Normally, the slip planes are found, slip planes are those planes between the two layers of atoms which are most densely packed. Okay. Once they are most densely packed, that means the resistance to the slip in between them will be less, okay, because they are very dense and they cannot actually resist further deformation. Okay. So, therefore, the slip planes occur, or the deformation occurs, slip line occurs between the layers which are most densely packed. Okay. Now, that are densely packed also, they are also farthest apart. That is another reason why we are saying that the deformation or the resistance to the deformation is less. So, the deformation occurs in between those planes, okay, because they are farthest apart, since they are most densely packed. Now, in any material you can actually find such a plane where you have most densely packed atoms. Let us take an example. Suppose here, as you can see, this is a face centered cube. Okay. So, face centered cube, as you know, the popularly known as FCC. So, here on each face, okay, at the center, that is why it is called the face centered cube. So, there is an atom. On this face there is an atom, on this face, okay, which is not visible here, dotted line, by dotted line it is shown that there is an atom. On the front face there is an atom, at the back there is one, at this there is one, and at the bottom there is one. So, now if you draw a line between these 2 points and these points, then you will see that this plane which is shown here, this is hatched. So, along this plane or on this plane you will have 1, 2, 3, 4, 5, 6, 7, 8, 9 atoms. So, you cannot draw any other plane where you will have more than 9 atoms. So, that is the plane we call as most densely packed atoms, meaning that number of atoms on that plane will be much more than on the other planes. Okay. So, then between those two planes, distance between those two planes will be more because they are farthest, because they are densely packed, and therefore, the deformation, resistance to deformation will be less, and therefore, along this the deformation occurs, plastic deformation occurs, and these are the planes which are called the slip planes, and along that line along which the deformation occurs is called the slip line. Okay. Now, let us say mechanism to continue how slip occurs. When two atoms are sufficiently close to each other, the outer electrons are shared by both the nuclei. You understand that. Suppose you have an atom here, okay, this is the nuclei, this is the electron, let us say, and there is one atom, another atom which is very close, this is the nuclei of that atom. So, in that case this outer electron will be shared by both the nuclei. Let us say this is a nuclei of one atom, this is a nuclei of another atom, and this electron will be shared by both of them. Okay. Now, what happens that there is an attractive force here between the electron and the neutron, and between the neutrons there is a repulsive force. So, therefore, the atoms do not collapse, okay, because the electron is attracted by the neutron. Okay. Now, they are not collapsed because as the two atoms they are coming closer to each other, all right, then there is a repulsive force between the neutrons. And here what happens, I have shown it to you through a curve. Let us say this is the force, and in the x axis if we put the interatomic distance, and interatomic distance is that distance between the two atoms, then you will see that the repulsive nature of the attractive force, that how they are attracting each other, it actually goes like this. Attractive force will be more when they are coming closer to each other. This is obvious. As they are coming closer to each other, the attractive force will be more and more because they are closer. All right. Similarly, as they are coming closer to each other, the repulsive force will also increase. All right. So, the repulsive force nature will be like this, as it is shown here, that at less interatomic distance the repulsive force will be more, at less interactive distance the attractive force will be more, and as the distance is increasing, the force, both attractive force and the repulsive force, they actually decrease. Now, at a certain point you will see that these two curves are intersecting each other. Okay. So, therefore, what happens in this, that at this point the atoms will be in equilibrium position. Okay. Now, in this therefore, when the atoms are in the equilibrium position in a lattice structure, that means either they have been deformed and they are in the equilibrium position, or they are not, they initially when the lattice structure is there, they are in the initial position or the uniform position, equilibrium position. There of course, the repulsive force and the attractive forces will be the same, and the reason I have shown it to you here. Okay. Now, when two atoms are sufficiently close to each other, the outer electrons are shared, as I said. Now, the result is that attractive force between the two atoms and the repulsive force, when two nuclei come very close to each other, there will be an attractive force, okay. There will be a repulsive force, as I explained. Now, these atoms form a polycrystalline solid with atoms in equilibrium position. All right. So, all these are grains, each of these is a grain, and in each grain has the lattice structure where atoms are in the equilibrium position. Okay. Now, The crystals, this is a polycrystalline solid. So, this is, let us say this is a crystal. So, these crystals are not perfect, that is the lattices are not without the imperfection. Okay. Now, what are the imperfections? Imperfections are the defects, also known as the defects. So, the imperfections may be point defect, may be line defect, may be surface defect. This you must have studied in somewhere in the material course, that any crystal may have this kind of defect. So, what is that? What are those defects? What does it mean? Let us take examples here. Point defect. Point defect may be either vacancy or interstitial impurity or substitutional impurity. Okay. Now, what is vacancy is that here is a lattice structure, as you can see, and all of a sudden in this lattice structure one atom is missing. Okay. So, that missing atom has created a vacancy, this place is vacant, all right. Or for example, in this lattice structure where otherwise the atoms are in equilibrium position, in one place the one atom is taking an abnormal position. Okay. All these atoms are in the normal position in their lattice structure, but this atom, as you can see, that this atom is taking an abnormal position. So, this is the imperfection or the defect, that is called the interstitial impurity. And here if you see, in this lattice structure equilibrium position otherwise, in one place there is a foreign atom, meaning this atom is not of this material, this is somewhere it is coming from, and it's occupying the space, occupying the place of the atom, okay, native atom, let us say. So, this kind of defect or imperfection is called the substitutional impurity. Now, there could be line defect, or line defects are also called the dislocation. Okay. If dislocation or line defect is that when the imperfection extending, if one imperfection, that is it can be a point defect, when this extends along a line has a length much larger than the lattice spacing. Okay. So, there is the lattice spacing here. Now, imperfection that extends along a line, so entire lattice has a lattice spacing. Okay. So, the imperfection if it goes beyond that line, beyond that length, then it is called the line defect, and surface defect is when an imperfection extends over its surface. Now, this is also called in some books you will find that this is called the twinning, all right, meaning that when the deformed surface looks like a mirror image of the undeformed surface. Okay. So, this is called the surface defect, meaning that when the imperfection is all over the surface. So, the line defect is along a line, okay, and the surface defect is along a surface. The rest of the things we will discuss in our next discussion session.